Welcome back, folks. This is MACM 101, Discrete Mathematics, Tutorial 9. Last week, you learned the mathematical induction, strong induction, and structural induction. This week, we are going to talk about the fundamental principle of counting. You will learn the permutations and combinations. Let's have a look at the first question together. In the first question, it provides us with a scenario that the board of directors of a pharmaceutical corporation has 10 members. An upcoming stockholders meeting is scheduled to approve a new slate of company officers, choosing from the 10 board members. The question 1 asks how many different slates consisting of the president, vice president, secretary, and treasurer can be board present to the stockholders for their approval. So when you get this question, you want to choose the president from the candidates, and then the vice president, the secretary, or treasurer. Or maybe you want to choose the secretary first. It doesn't matter. So let us try to choose the president first, because we have 10 members. So there are 10 candidates for the president. So let me write down president. We have 10. And if we choose one member from 10 members, then we have 9 remaining. So 9 candidates for the vice president. So we have 9 for the vice president. Similarly, we have 8 for the secretary and 7 for the treasurer. So the total ways of select the president, vice president, secretary, and treasurer could be 10 times 9 times 8 times 7. We have 5,040. So that's 5,040 different slates for the president, vice president, secretary, and treasurer. And for the question B, they ask 3 members of the board are physicians. How many slates from the part A have 1. A physician nominated for their presidency. 2. Exactly 1 physician appearing on the slate. 3. At least 1 physician appeared on the slate. So if it restricts a physician nominated for their presidency, we have only 3 choices for the president. So we have 3 for the president. Sorry, but others will remain the same. It will, so if we choose 1 member from the 10 members, we have 9 for the vice president. So we have 9 for the vice president, 8 for the secretary, and 7 for the treasurer. So we have 3 here because we only have 3 physicians, and the president must be the physician. So we have only 3 choices. And so we have 1,512 ways to make this slate. We have 1,512 different slates. And the question 2, it asks how exactly 1 physician appear on the slate. So this question is a little bit complex. So first, we have to choose 1 physician from 3 candidates. So we have 3 choose 1 here. And then we have to choose 1 slate for the selected physician. So we have 4 choose 1, because the physician could be president, vice president, secretary, or the treasurer. So the expression should be 3 choose 1, 4 choose 1, and times 7 times 6 times 5. It starts from 7 since we only allowed 1 physician. So we have to subtract the 3 physicians from the candidates for the vice president or something. The remaining positions. So from this equation, we have 2,520 different ways. The question 3 is at least one physicant can appear on the slate. So in this question, we have to include at least one physicant. So we can subtract the possible slates such that no physicant is selected from all possibles. If no physicant is selected, we have 7 times 6 times 5 times 4 is 840. And we have all possible slates in A is 5,040. So the result for at least one physicant pair is 5,040 minus 840. 840 is just 4,200. That's the question 1. Question 2 asks you how many arrangements are there of all the letters in the sociological. In this question, you have to find the duplicated letters first. We have 3 O's, 2 I's, 2 C's, and 2 L's. Simply, if we have 12 different letters, we have 12 factorial possible arrangement. But here, we have to subtract the duplicate patterns. So first, we do the permutation for 12 different letters. It's just 12 factorial. And we have to subtract the duplicate patterns. So we want to divide it by the duplicate letters. If we have 3 O's, we may have 3 factorial ways to arrange this 3 letter. So we need to divide it by 3 factorial. And we have 2 I's, we have to divide it by 2 factorial. And 2 C's, same thing apply to the L's. So the result could be 9,979,200. So it's 9,979,200. That's the question 2. In the third question, it asks, in how many different orders can 5 runners finish a race if no test allowed? If you are not sure to use permutation or combination, you just ask yourselves, if the order important? If the order matter, then use the permutation. If the order doesn't matter, then use combination. In this question, we know the order of the runner arriving is matter. So we have to use the permutation. Then we have P5, 5, because we want to permute 5 runners. Or say we have 5 different slots and we have 5 candidates. So it's permutation of 5 and 5. It's just 5 factorial divided by 5 minus 5 factorial, just 5 factorial, equals to 120. Or you understand what behind it saying is just a 5 factorial. Question 4. In how many ways can 12 different books be distributed among 4 children so that A, each child got 3 books, B, the 2 oldest children got 4 books each, and the 2 youngest got 2 books each? The question A, we have for the first child, we have 12 books. So there are 12 choose 3 ways to choose the book. For the second child, we have 9 remaining. So we have 9 choose 3. Then the third child will be 6 choose 3. And for the last one, he or she will take all the remaining books. So As I said, sorry, for the first child, we have 12 choose 3. And the second one, because we have choose 3 books out of 12, we have 9 remaining. So we will be 9 choose 3 and 6 choose 3. Then because the last child will take all remaining, so there only one way. And the result could be 220 times 84 times 20. So it could be 369,600. Yep. The question B, similarly, but for the 2 oldest children, we have 12 choose 4 and 8 choose 4, right? Because we want assign 4 books for the oldest, or call the oldest 1 and oldest 2. We have 12 choose 4 and 8 choose 4 for each of them, and we have 4 remaining, and the youngest got 2 books each. So for the youngest one, we have 4 choose 2, and the last one take all the remaining. So we have the 12 choose 4 is 495, and 8 choose 4 is 70, and we have 6 is 207,900. That's the question 4. The scenario of question 5 is the college food plan allows a student to choose 3 pieces of fruit every day. The fruit available are apples, bananas, pears, and plums. For how many days can a student make a different selection? So we have 5 cans of fruits, and each day we can pick 3 out of them. Similarly, check if they order matter. We don't care about which day consume what combo, right? So we will use the combination. And because we have 5 candidates and we want to choose 3 each day. So we have 5 choose 3 is equal to 5 factorial times 3 factorial and 5 minus 3 factorial. And we have 10 different combos. That means if we choose 3 out of 5, then we got 10 different ways to make this combination or make the selection. That means we can so that means a student make a different selection for each 10 days. That's the answer for the question 5. Question 6. In how many ways can 5 identical candy bars be distributed among 5 children, with the restriction that the youngest get only 1 or 2? This question is a little bit difficult. You have to understand what's behind this thing. Before that, I would like to show you a classic question. So let's have a look at this question. Suppose we have 5 identical objects. We want to put them in 3 distinct bins. So what do we have here? Just 5 identical objects. And we want to put them in 3 bins, which means we need 2 dividers. If we insert 1 divider here and 1 divider here, we have the 1 object in the first bin, the 2 in 2, and 2 in 3, right? But we also have some possibility that the first and the third has nothing, right? Or maybe the second has nothing. It's possible, right? So what actually we do here is we assume we have 7 different spots. and we want to put 2 dividers into the spot. Then you can see we have 1 in the first bins, 2 in the second bin, and 3 in the third bin. Or if we put the divider here, you know the third bin has nothing. This question is similar to the example 1.3.4 in textbook. We know that for m identical objects distributed to n distinct containers, we have m plus n minus 1 choose n with repetition. So if you, I suggest you to have a look at the example 1.3.4 in the textbook. And so we got this formula. Right, let's go back to the question 6. In this question, we have a OR here, which means we have to split it into 2 conditions, and we sum up the possibilities. So the first scenario, we have the youngest get only 1. If the youngest get only 1, we can consider that it distribute 14 identical bars to 4 distinct children. So by the formula from the textbook, we have m plus n minus 1 choose n, which means we have 14 because we distribute 1 bar to the youngest children. Plus 4 minus 1 choose 14. Right? It's same as 17 choose 14 and 860. Or you can maybe you can think this in another way, like by the symmetric property, 17 choose 14 is just a 17 choose 3. In this way is similar as what we talk about in the classic question. You put 3 dividers in 17 spots. Then if you put 3 dividers in 17 spots, you got the 680 ways to put the dividers. And by the symmetric property, 17 choose 3 is just like 17 choose 14. So the 680 ways to put the dividers is similar as distribute 14 identical bars to 4 distinct children. That is if the youngest get only 1. If the youngest get 2, it's just same as 1, but we have 3 bars remaining. We have 4 children's, so we have 13 plus 4 minus 1 choose 13, since the youngest child got 2 bars, right? This is 560. Thus the result will be the 17 choose 14 plus 16 choose 13 equals to 1240. That's the result. In the question 7, you're going to toss 3 fair 6-sided dice, and the number showing on the top are recorded. So I have 3 questions. The first question asks you how many different records sequence are possible, and the second is how many of the records contain exactly 1/6, and the third is how many of the records contains exactly 2/4. So let's have a look at the first one. If you toss 3 different, if you toss 3 fair dice, you have 6 possible results for each dice, right? So it's just 6 to the 3, 6 cube. It's 216, right? Because for the first dice you have 6 possibility, and for the second dice you have 6, and third dice you have 6, and all the resulting independent, and you times them together, you got 6 cube is just 216. For the question B, how many of the records contain exactly 1/6? So if you want exactly 1/6, we have three choose one ways, since first one is 6, or second one is 6, or third one is 6. So we have to choose one from these 3 dice. And for the remaining 2, we have 5 square. Why? Because if the first one is 6, we already got the 6. So, and the question asks, the records contain exactly 1/6. We cannot have another 6. So we have only 5 possible results for the second dice, and 5 for the third. So, and similarly, same applies to the second, if the second has the 6, or the third has the 6. It's just a 3 choose 1 times 5 cube. It's just 75 records. And the question C, it asks how many of the records contain exactly 2 4s. So similarly, there are 3 ways to toast exactly 2 4s. Why? Because you can have the first and second, the first third, and the second and third. So you have 3 ways to toast exactly exactly 2 4s. If we have exactly 2 4s for the dices, we will have 5 possible outcome for the last one. So we have 3 times 5 equals to 15 records, right? That's the question 7. Question 8, it asks you how many ways can you choose 3 of 7 fiction books and 2 of 6 non-fiction books to take with you on your vacation. In this question, the order doesn't matter, right? So we choose the combination, right? And combination means you choose 3 out of 7 and 2 out of 6. So we have 7 choose 3 fiction books, and 6 choose 2. We got 35 times 15 is 525. That's the answer. It's very simple. Very, very simple. We don't include too difficult questions in this tutorial because you only learn the fundamental principle of counting. I think the only difficult question in the tutorial is question 6. But if you read the example on the textbook carefully, that won't be a problem, right? Because the textbook explain the question and the logic very clearly. And if you know the formula for the combination with repetition, that could be easy. And I'm not sure if you have time to include some complex or difficult theorem or logic of the counting in this course this term. But if you want to learn something behind the scene, like the multinomial, the question 6 is just the multinomial, and the combination, you have learned a binomial theorem or something. Maybe you will learn this in the statistics course. But for the MACM 101, the discrete mathematics, I don't think you will face too difficult question about the combination and permutation. Yeah, that's all for this tutorial. Thank you.